Hi, and welcome to the AMIA Clinical Informatics Board Review course. This is Db Desai giving Lecture 3A2, or Systems, Databases, and Networks. Here's the reference to the relevant sections in the core content. We're looking at sections 3.1.2 and 3.1.3, Architecture and Networks. Here's all the topics I intend to cover. Here's many of the key concepts that we'll cover during this talk. And here's the sequence we'll follow from the beginning to the end of the lecture. So let's define what a database is. A database is any collection of related data. These could be as straightforward as an address book or a spreadsheet or a Microsoft Access database. And typically what we see implemented around databases is something called a database management system, or a DBMS. The function of a DBMS is to allow users to interact with the database and to maintain the structure and integrity of that database. Common features of DBMSs are that they allow you to constrain data types and structures. So for example, I can define that a specific column always has to be an integer, or a specific column always has to be a date. Maybe some column can never be blank, or some column can only be populated by increasing sequential integers like an index of some kind. They allow you to construct data tables and to store data on a storage medium, whether it's tape or magnetic disk or something like that. And then there's really basically four functions that all databases must allow you to do, which are to create, retrieve, update, and delete, or insert, read, edit, and delete the data in the database. And these functions are so commonplace that often you'll hear programmers refer to these as the CRUD functions, for create, retrieve, update, and delete. Most DBMSs have a way to allow data sharing between users. So if I have a set of data tables and you have a set of data tables, I can control the permission and visibility of those to other users. They also should allow you to control concurrency. So if two people are querying the same data structure, or if they're submitting or updating data to the same structure, you need to have a way to make sure that there's no collisions and overwrites. Then you need to be able to protect against inappropriate access, so there has to be security overlaid on top of this. Maybe there's reason why you want to obscure specific columns in a view to specific users. And they should be fault tolerant and allow for hardware and software failures to make sure that they don't wipe out your data. Finally, DBMSs should have a mechanism to maintain and optimize data structures, so performance tuning and indexing and reclaiming unused space, for example. So the simplest type of database that I can think of is a flat file, and all of us have used these, maybe we're guilty of using these. They are convenient, they're easy to use, they are all over the place. So your typical Excel spreadsheet that you use for just a quick and dirty flat database is an example of this. The problem with these is that they often require redundant data. As soon as you introduce any kind of dimensionality into your data source, you have to consider the possibility of redundancy. So for example, let's say in our flat file here that we had 2 rows for Louise Chen. You'll notice that I've indicated that she's deceased. If she exists in more than one place in this spreadsheet, then you have to remember in both places to have the correct status for whether she's deceased or not, and in both places to make sure that she has the same date of birth, for example. Also, you can see how in this example I have 1 row for Louise, but I want to be able to indicate that she's on 2 medications, and I can't easily do that with a flat file. And so in my example here, I've sort of shoved 2 medications into 1 cell. You have sort of limited ability to enforce data integrity. Of course, Microsoft Excel that many of us use, it's sort of the de facto standard for some of these things, does allow you to put some constraints on the data types, but in general, a flat file, this is not one of its key strengths to enforce data integrity. And so I've tried to demonstrate that in this example with the multiple spellings of yes and no. Some people are putting this as lowercase y versus all caps yes. That there's no, because I've stored it as basically a text string, there's no consistency in how people are doing it. Another vulnerability of flat files is that if you have intentionally incomplete data, you basically have to represent it as blank cells. So what's the alternative? Well, and one of the alternatives is this idea of a relational database. And here you can consider multiple smaller flat files that are associated or related to one another in very in well-described ways. So in relational databases, the relation is analogous to what we would call a table. Each relation has an attribute, which we think of as the columns in the table that correspond to a specific domain. Each relation has 0, 1, or more tuples. A tuple is what we would think of as a row. And the key thing here is that a tuple is an ordered list of elements. In other words, the order is important. You can't just mix up the sequence of the elements, because then they'll be in the wrong, you'll have the wrong attributes in the wrong cells. And the tuple is comprised of various elements, one for each attribute. And again, we think of elements as being the cells. So this there's 4 terms here that you should know: relations, attribute, tuples, and elements, which are the same thing as tables, columns, rows, and cells. Typically, the elements are constrained to a data type that's consistent across that attribute. So every attribute for date of birth is stored as a date field. Every attribute for first name is stored as a character field, and so on. Attributes can also have constraints. You can enforce that they are not null, or you basically force somebody to require somebody to enter a value for them. They can be auto-incrementing. Maybe you have a list of patients and you want to sequentially number them from 1 to infinity, that you want to have at least one column in there that corresponds to that auto-incrementing value. You can have something called a cascading delete, which means, let's say that you have the same attribute represented in a number of different relations, and I want to be able to enforce that if I delete a tuple from one row, that everywhere else where that entity is represented in other tables, those deletes kind of cascade their way through the other tables as well. And then the most significant type of constraint are these primary key and foreign key relationships. And we're going to spend a lot of time talking about what those mean. But basically, that's the foundation of how you coordinate or relate these tables. That's the relational part of relational database, as it's described through primary and foreign keys. If I wanted to describe the structure and these constraints of a table so that somebody else could pick up and implement their own copy of my own table, I can do so through a metadata language called Data Definition Language, or DDL. And again, metadata means data about the data. The DDL, while it describes the structure and organization of the table, may not actually define the individual attributes and what they mean at what we call the semantic layer. So the actual real-life meaning of a specific attribute is specified in something called the data dictionary. And this has not just the foreign key and primary key constraints, but also the definitions of each field and its intended use. So if you had, for example, a table that had a whole bunch of clinical quality measures, the DDL would describe the structure of the table. The data dictionary would actually define those clinical quality measures and what they represent in real life. The table schema, or the relational schema, is the description of how all of those individual relations are connected to one another. So that's basically the sort of master metadata about an instance of a database. And if I have that schema and I want to basically populate my own version of it, I'm creating an instance of that schema. Now, that should remind you, this idea of having a schema that you instantiate should remind you a lot of object-oriented programming. And we're going to keep drawing that corollary between relational databases and object-oriented programming concepts, because I think it's a very meaningful analogy. One of the nice things about a relational database is if I want to introduce a new attribute, into the model, all I have to do is add a new column to the table. And because all of the attributes for a specific table are easy to find in one table, in a very simplistic way, the relational database allows you to know everything that contains or possesses one attribute. So for example, if I have a table of all the patients in my electronic health record, and I want to identify every single patient who comes from a specific zip code, there's probably exactly one attribute in one table that specifies the zip code. And with a single line of SQL query, structured query language, I can actually identify every single patient that matches that criterion. Let's continue this analogy between databases and object-oriented programming. There is this class of software called Object Relational Mapping, or ORM mapping tools. And what ORM does is it takes all of the useful things about your objects and maps them to all the useful functions of a relational database. So consider this, if I'm writing a program in an object-oriented programming language that involves a class of patients, and I'm going to create an instance of a patient every time I register a new patient. That class of patients might relate to a specific table in my database. And whenever I instantiate a patient in the software, I probably want to add a tuple in the relation in the database. And every time I populate an attribute on the patient, like their date of birth, I want it to be reflected in the database itself. So there is this useful analogy where the class of in an object-oriented programming language is similar to a relation in a database table. An instance of that class is just like a specific tuple or an instance of that row in a relation. And then attributes are the same, that the attribute of the class is the same as the attribute of the relation. You can think of those accessors and mutators, the getters and setter functions that we've discussed in the programming lecture, as being analogous to the CRUD functions. So when I want to get the patient's medical record number, I'm basically retrieving it from the database. So because there is this natural analogy between object-oriented concepts and relational databases, and because people would do this all the time, they didn't want to have to define the methods in the SQL code for how to perform the different object-related the different accessor and mutator tasks in their OOP programming language. It's simple to sort of stick this ORM computer program in the middle, where as soon as I create a class, the ORM will automatically create a relation in the database. As soon as I populate it with an instance of the class, the ORM will automatically create a tuple in the relation. And as soon as I start using my getters and setters in my class, those are mapped automatically to the CRUD functions in the relational database. So let's look at a sample schema. I've got two tables here, a patient and an order table. And the patient table has 5 attributes: patient ID, first name, last name, date of birth, and is deceased. And the order table has 3 attributes: order ID, med name, and patient ID. And what I specified here is the patient ID must be an integer. The first name and last name must be a character string of variable length up to a maximum of 50 characters. That's what varchar 50 stands for. The date of birth is stored as a date, not as a text field, as a date. And is deceased, I'm storing as a Boolean. I expect a true or false value, and those are the only values I can accept into here. So already this has cleaned up some of the vulnerabilities of that flat file that we had. We're standardizing the data type for each of these things. And I've also introduced this new idea of a primary identifier. So you notice that patient ID, the integer value there, is a unique. I'd probably want to have another constraint that says this has to be a unique value as the primary key for the patient ID. And that uniquely identifies every distinct patient in the relation. In the order table, I have an order ID, which is an integer, and that happens to be the primary key for this table. So that identifier, order ID, identifies every unique order. Now, this is a fairly straightforward example, but I'm going to store the medication name as a varchar 50, a variable character string of length maximum 50. And then I've introduced this third attribute, which is patient ID, an integer. And you might be thinking, well, why do you need patient ID in this table? If you look to the left, you can see that I've indicated that it's a foreign key to pat ID in the patient table. And this is our relation. This is how I am specifying in the schema that the patient table and the order table are related. I'm saying that the patient ID attribute in the order table must correspond to a primary key of patient ID in the patient table. Okay, now here's an example of our relational instance. So I took that schema, I've created an instance of that database with that simple two-table schema, and now I've populated the tables with a bunch of tuples. So the patient table has 4 tuples representing 4 different patients, and the order table has 5 tuples representing 5 different patients. In this example, I've made the patient ID sequential and the order ID sequential. That's actually not required, nor is it recommended. You really should not have a pattern for those, but for simplicity's sake, that's what I've done here. And you can see, for example, Louise Chen now has her own patient ID, 1004. I've split apart her first name and her last name so I can reuse them in different ways in the future. I've constrained her date of birth to a date field, and I've indicated with a simple Boolean value whether she's deceased or not. In the order table, I'm doing the same thing. And notice how I represented the fact that Louise is on 2 different medications. So there's 5 medications there for 4 patients. One of the patient IDs is duplicated. That's 1004. They correspond to order ID 993 and 994. So this means that acetaminophen is associated with Louise Chen, as is topiramate. So now I have a clean way of representing what we call that one-to-many relationship, that one patient can have many medications. And if we want to start manipulating this table and actually finding data that's in there, we have to turn to structured query language, or SQL, often pronounced as SQL. And this is the one programming language that you'll have to know for the board examination. So I mentioned the programming course that you probably don't need to know Java or JavaScript or any specific object-oriented programming language. You might be expected to know pseudocode or some really, really straightforward-looking example of a simpler programming language, but you definitely need to know SQL. So we're going to spend a good amount of time going through these examples, and my goal for you is that you should know exactly how I got the answers to every single one of these questions, and you should be able to answer them on your own. So the advantage of SQL is, well, let me go back up a little bit. SQL represents a family of related languages with slightly different dialects. So Microsoft SQL is slightly different from Oracle SQL, is slightly different from the open source MySQL, but they all share the basic English keywords that allow for the basic CRUD functions. They may implement certain things slightly differently, but for the most part, they're all like dialects of the same computer language. So the basic CRUD functions, this is the syntax for them in SQL. Insert into, then the name of a table, values, and then the ordered list of the tuple. And remember, it has to be an ordered list in the correct order. Otherwise, you'll populate the wrong attributes, the wrong elements into the wrong attributes. The select statement is read select, and then the list of columns that you want to select, from, followed by the name of the table, where, and then any constraints you want to implement. Select, patient first name and last name from the patient table where last name starts with the letter D, for example. Update is one of your CRUD functions. So you want to update followed by the name of the table, set the name of the column equal to some value, where, and then there's a condition. So that one's probably the most complicated of these syntaxes. And then delete from has this syntax, delete from the table, specify the name of the table, where some column value equals some value. All right, so here's that same two-table schema. We've described in the schema, this is the instance, we described in the schema what the primary key foreign key relationship was. You remember that pat ID is the primary key for the patient table, order ID is the primary key for the order table, and pat ID in the order table is a foreign key to pat ID in the patient table. So let's write a select statement that returns the data from both tables. This is an example of that syntax. Select patient.firstname, comma, patient.lastname, comma, order.medname. And notice that I'm treating this just like an object-oriented class, where if I think of the patient class, if I want to access the attribute, I put a period and then the name of the attribute. So I'm saying find the first name from the patient table, the last name from the patient table, and the med name from the order table. And that's what that dot notation refers to. So that's the select part of it. The second part of the select statement is I have to say from a table. And I'm going to teach you how to do this using a join statement. So select those things from the patient table, inner join order on patient.patid equals order.patid. Inner join, that's an interesting thing. It's a new concept. Notice that my from statement only contains one table, the patient table. So I basically have to tell the SQL interpreter how this table is related to the order table, and specifically because I've got an attribute from the order table in my select statement in that first line. And if I didn't have that join, it would error out and say that it can't find that table. So, and then after the words inner join order, which refers to the order table, I have to tell the SQL interpreter how those two relations are linked. So join them on these attributes where patient.patid is equal to order.patid. So all I'm doing is restating what that primary key foreign key relationship is. And that is my SQL query. If I execute that query, this is the list I'll get. I'll get a table at the command line or at the console that'll say first name, last name, med name, John Smith, propranolol, Jane Doe, diphenhydramine, Jose Patel, amoxicillin, Louise Chen, acetaminophen, Louise Chen, topiramate. And notice that as we expected, or as we wanted, Louise Chen appears twice because there are two conditions that satisfy that inner join constraint of patient.patid equals order.patid. There's two combinations that allow for that. So now we have a nice way of being able to query these SQL tables and make use of that foreign key, primary key relationship. Notice that I could have written this join as a where clause, and these two would be semantically equivalent. They would have the same output. So I could have said select patient first name, patient last name, order.medname from, if you're looking on the right side, patient, comma, order. Notice that I've listed both tables, but I still need to specify how patient and order are linked. So I can say where patient.patid equals order.patid. Okay, this works great for inner joins, but this does not work for any kind of join where you want to see the null values, because you can't do that with a where statement. You can probably sort of intuit why the left flavor of this we can coerce into showing null values, but the right version of this we cannot. So what about those null values? Well, that's when we have to get into the difference between inner versus outer joins. If you want to join a table where there's not a one-to-one equivalence, where not every row in A has a match in B, and not every row in B has a match in A, how do we do that? As we showed in the earlier example, the inner join will only include rows that match both tables. So let's look at this new schema, or this new instance of a schema. I've got two tables, faculty and interests. And in the first one, I've got the user ID as the primary key and a list of 5 faculty members' names: Tom Payne, Alexis Carter, Bill Hirsch, Db Desai, and Pesha Rubinstein. And then on the right side, I have the things that those people are interested in, their hobbies: hiking, languages, guitar, home improvement, and reading. And what I'm implying by having user ID as a column there is that that's the foreign key that goes back to faculty table. So you can see that, for example, Tom Payne, user ID 54, likes to hike. Alexis Carter, user ID 30, likes languages. Bill Hirsch, user ID 41, likes to play guitar. Apparently, I have no interests. There's no 29 in the right table. And Pesha likes to read. Conversely, there is a hobby for home improvement that links to a user 61 who's not present in our faculty table. So we have a faculty member who doesn't have an interest and an interest that lacks a faculty member. So if I did the inner join, remember it would only return the results that satisfy that constraint in both directions. If I did our typical inner join syntax, select faculty username, comma, interest.hobby from faculty inner join interests on that constraint right there, I would only get 4 rows. I'd get Tom Paine, hiking, Alexis Carter, languages, Bill Hirsch, guitar, Pesha Rubinstein, reading. But I might have reason to intentionally show the null values. Maybe I want to show every faculty member, even the ones that have no interest. Maybe I want to show all the hobbies, even the ones that are not preferred by a faculty member. Right, so there's the 4 rows that matched, and you can see there's nothing that matches the missing faculty or missing interest. Well, what if we changed it from inner join to this new phrase, left outer join? That would include all the rows in the left table, even if it forces us to display a blank cell in the right table. So this is the example where I want to see all faculty members regardless of their interests. All I've done is slightly change the syntax, select faculty.username interest.hobby from faculty left outer join interests on faculty.userid equal interest.userid. And now, voila, I can see my missing cell or my null value in the interest column. And if you're following along, you guessed it, if I change this to right outer join, I can show all the rows in the right table, the interest table, and force it to show null values in the left table. The logical question you're probably asking is, which one's the left table and which one's the right table? It's not just the ones that I've shown left and right in that top picture. Well, it turns out the left table is the one that's in your your from statement, and the right table is the one you're joining to. So that's a clean way to keep track of it. And again, if I change the syntax just slightly to right outer join, now I can see home improvement and that there's no faculty member with that interest. There's another variation on this, and it's called the full outer join. Just as you would expect, if I change this to full outer join, now I can see nulls on both sides, and here they are, that there's no faculty member who has an interest in home improvement, and I have no interests, apparently. The only other flavor of join is this thing called a cross join. And notice that the cross join does not have a constraint. I don't have to say where faculty.id equals whatever we did on the previous screen. I can just stop at the phrase cross join interests. This query, using the example table from the previous slide, would actually return 25 rows. And the question to you is, why would it do that, and why might that even be useful? Well, it's basically doing the cross product or the Cartesian join of both of these tables. So it'll say, each faculty member with each of the 5 hobbies, that'll be the first 5 rows. Then it'll go to the second faculty member with each of the next 5 hobbies, that'll be the next 5 rows, and so on and so forth. So you end up getting 5 times 5 or 25 different rows. The only time, honestly, that I've seen this used is if you want to create a whole bunch of test data. You want to create data that looks like real clinical data, or just generate massive amounts of things that look like regular data. Perhaps you're trying to do some load testing or something like that. But this is not really a useful thing if you're trying to retrieve data. For some people, this idea of left and right joins is a little bit confusing, the inner, outer, and so on. So I'm going to offer a couple of different ways to think about this. In addition to left, right, and the tables that we showed before, for some people who are visual, think about these as Venn diagrams is useful. So imagine you've got a table A and a table B. The inner join of those two tables will only return the intersection. So it's like doing the AND operator on them. And so you won't see any of the values where there's a null in A or a null in B. The left outer join will show you everything in A, regardless of whether column B is null or not. The right outer join shows you everything in B, regardless of whether there's a null in A or not. And then the full outer join shows you everything from both tables. So it's like the OR Boolean operator. So one nice thing about SQL is you can actually do nested queries, and basically you can mimic an inner join using one of these nested queries. Where might this be useful? Well, let's say I don't want to deal with the join logic, or I want to be able to modify the second, maybe I have some more complicated selection criteria for that second table. So here's one way I can do it. Suppose that I want to look in a table for medications that contains a patient ID called pat_ID, and I want to find all the meds that we prescribed on patients between ages 4 and 5. Well, logically, the first step I want to do is I need to identify all the patients who are between 4 and 5 years of age. So that's the line that's in red there. This is my subquery. So by itself, that stands as its own select statement. Select pat ID from patients where pat age between 4 and 5. And notice that I've wrapped that in these parentheses, and I'm passing that to the outer query as the name of a table, or the relation specified in the where clause. So when you run that little red query on the inside, SQL doesn't distinguish between that result set and any other table that you might include in a where clause. So I can basically substitute it for the name of a table in the outer clause. So now I've got select, and I've got a wildcard operator there, sorry, an asterisk there, which means everything. Select everything, all the attributes from medications where a patient ID is in, and then here where it expects the name of a table, I'm actually inserting another subquery. So this would actually give me the list of all medications where the patient is between 4 and 5 years of age. I think this is a valuable thing to look at and make sure you understand why this returns the desired data that we want. Okay, let's look at a more elaborate example. I've got two tables here that represent customers and orders. There's 5 customers: Alexis, Beemal, Tom, Bill, and Pesha, and they have their own primary key. They live in 5 different cities: Atlanta, Philadelphia, Seattle, Portland, and Bethesda. There are 5 orders: 65, 66, 67, 68, 69, that represent 5 different customers: 2, 5, 7, 1, and 3. And there's an item description of what they bought. This is from some online shoe store. And you can see customer ID is a foreign key to ID in the customer table. So now let's write a query that returns the order ID from the right table there, the name of the customer from the left table, and the city of all the customers who ordered dancing shoes. So we only want the order ID, name, and city of people who ordered dancing shoes. And I think it's useful, when you scan through this, to see that there's exactly one customer who ordered dancing shoes. It's customer 5. So we can expect that this is going to show us 66, Pesha, Bethesda, we think. Let's see if we're right. So we're going to write our select statement. Remember, we're going to use that dot notation because there are redundant. Actually, it's always a good practice to reference your tables by saying the name of the table, dot, and the name of the attribute, even if you're only doing a query from within a single table. But you absolutely should do it if you're doing queries between tables, because you may have the same named attribute in 2 different tables, and then the SQL interpreter won't know which one you're talking about. So the first line is going to be our select statement: select orders.orderID, customers.name, customers.city. That's directly from the question itself. That's this sequence of the attributes that they asked us to show in the query. Now we have to choose a from table. And the important thing here is that it doesn't matter which one you choose as your from table, because if you choose one as your left, and the other one's going to be your right, and vice versa. If you choose the orders table, you have to join it to customers. If you choose the customers table, you have to join it to orders. So just for convenience, because orders is the first attribute in here, let's just choose orders. So In this case, the problem didn't say anything about showing nulls, so we're fine doing an inner join. So I've got select orders.orderID, customers.name, customers.city from orders, inner join customers, and now I have to specify their foreign key primary key relation on orders.customerID equals customers.id. So far, so good. In fact, here's what we have so far. And now the only thing that's missing is our where constraint, where we have to constrain the results as was described in the question to the orders where the item description is dancing shoes. And here's our complete query. Notice that all I added at the end was where orders.item description equals dancing shoes in single quotes. That's typical for SQL where you need single quotes. And just as we had predicted, if we run this query against this instance, you get 66 Pesha Bethesda. It's the only it's the only tuple that can satisfy those constraints in that join criteria. Here's 4 bonus questions. I would encourage you to do these on your own before you advance the slides. The bonus questions are, can you modify the query to show only customers from Seattle? Can you modify the query to show only customers from Seattle who did not order golf cleats? Can you modify the query to show all orders, including those where the customer is not listed in the customer table? In other words, can we show the null customers? Can you modify the query to show all customers whose first name starts with the letter B, even if they did not place an order? All right, so let's tweak this to only show customers for Seattle. That one's straightforward. All I have to do is change my where clause. Same query, but now the where clause says where customers.city equals Seattle. And let's guess what the result of this is going to be. 69 Tom Seattle. So if you guessed that that was going to be the output, you were correct. Next question was, how do we show this to show only customers from Seattle who did not order golf cleats? And this is a little bit of a trick question. When you have multiple conditions in the where clause, the first one starts with where and all the others are joined with ands and ors, and you can group them with parentheses as necessary to match your join criteria. So in this case, what I do is where customers.city equals Seattle and orders.item description, and then I use the less than, greater than sign to mean not equal, and orders.item description is not equal to golf cleats. And what would this return? You guessed it, nothing. There are no rows that satisfy these constraints. There's no tuple that satisfies that constraint where the customer is from Seattle but did not buy golf cleats. All right, what about the missing customer? So the fact that they want to see nulls tells us that this has to be some kind of an outer join. And since orders is the left table in our from statement, then it must be a left outer join if we want to see null customers. So this is pretty straightforward. It's just these 4 lines. I've gotten rid of my where because there's no constraint on it. And now I can see that order ID 67 was not placed by somebody who's currently in the customers table, that there's no name and no city associated with that purchase. Apparently none of us like clogs. I'm going to introduce some new syntax here, the wildcard syntax, which is this %, and the phrase like, which is a condition to do some wildcard matching. So the question here is, how do you show all customers whose first name starts with the letter B, even those with no orders? So again, the even those with no orders tells us we need some kind of an outer join. In this case, if we're still going to keep the orders table as our from table, and we want to see null orders, we need a right outer join. So I've got select orders.orderID, customers.name, customers.city from orders, right outer join customers on orders.customerID equals customers.id. So that's our typical outer join syntax. And the only part that's different is now this like statement where customers.name like single quotes capital B %, single quotes. And what that basically means is that only show me the customer names that start with the letter B followed by any sequence of wildcard string after that. capital B, by the way. And there are two ways to satisfy that. So this query would actually return 65 Beamel Philadelphia because I ordered flip-flops. And then it would show blank Bill Portland because while Bill is in the customer table, there are no orders that match customer number 4. A few other tidbits about the like statement. First of all, that % matches a character string of any length. If you only want to match a single character, then you use the underscore. And so if I had a constraint like where last name like Smith underscore, it would match Smythe, Smiths, and Smithy, but it would not match Smith by itself because that underscore single character is mandatory. It must have at least one. It must have one additional character, and it would not match Smithers because it has more than one character at the end. Like is case sensitive, so if I wanted to correct for the fact that people might capitalize or lowercase various letters in their names, where I wasn't sure that somebody had entered it correctly, I could convert them all to uppercase or all to lowercase before I ran my query. So, for example, if I'd use this constraint where lower parentheses last name, so that's like a method that takes an attribute. In this case, the method is the lower method and the last name is the attribute. Where lower last name is like single quotes DESA %, single quotes, that would match my last name Desai, even if you capitalize the S or forgot to capitalize the D. It would match Desal because it's any number of characters that follows the A as specified by the % and so on. So lots of potential matches for that. So that's just a couple of variations on the like clause. All right, take a stretch, come back in a minute, we're going to keep going. Hierarchical databases. So these are totally different from relational databases. These are structurally different from relational databases because they're not organized into relations and tuples the way we think of. These are optimized for rapid transaction of hierarchical data, and in a very simplistic way, it allows you to know every attribute about one thing. For example, a highly dimensional type of data like a patient who possesses an address and a medication list and an allergy list and so on and so forth. If I organize that patient table into a hierarchy, I could basically quickly retrieve everything about that patient. Whereas if I tried this in a relational database, I'd have to go through hundreds of tables potentially and rejoin them in order to find all the information about exactly one patient. Computers are very good at traversing trees. They're very fast at this, and you can index them to make them even faster. And so typically the computer knows how to start from the root node in a tree like this, and quickly find the branch that it's looking for if you've indexed it correctly. So for example, a query like this, find all deceased patients who were ordered to Pyramate. That would be actually easier to do, quote unquote, in a relational database than it would be in a hierarchical database. Because in a relational database, I would go look through the patient table and find every patient who had a flag of deceased. So it would be a straightforward, maybe a couple of lines of SQL. In contrast, in the hierarchical database, it would have to go peek into every single node, traverse the tree all the way down to the medication attribute, look for the medication to Pyramate, go back up and go back down again to find out if they were deceased, and I have to do this for every single patient to create that list. So you can imagine there's certain types of queries where it's computationally advantageous to use a hierarchical database, and there's other kinds where it's advantageous to use a relational database. I actually think this is the reason why some of our contemporary electronic health record systems have two totally different databases. The one that's used for operational transactions, which might be something like cache for a hierarchical database purposes, where you need highly performant databases to be able to pull all the data about a single patient very rapidly and show it on a single screen, versus the reporting database, which might be in a relational table, a relational schema, so that you can do much more aggregate analysis, or queries like this: find every deceased patient who was ordered to be on topiramate. One of the inherent limitations of a hierarchy is that child nodes can only have one parent. So it's difficult to model these relationships between child nodes, this sort of many-to-many or recursive relationships, but not impossible. People have come up with techniques to overcome that. So here's an example of a hierarchical schema. And in all these examples, the flat file, the relational database, and now this one, I'm using the exact same data structures. So you should see, what you'll see here is that there's 3 patients: 1004, 1005, 1006. Patient 1004 has a medical record number, a date of birth, a first name of Louise, a last name of Chen, a deceased flag of yes, and then a medication array or a data structure. And this is, again, the sort of advantage of these hierarchical databases, that I can represent these highly dimensional structures simply by shoving more complex structures in at various branches of the tree. So the medication branch of the tree itself is its own mini tree that includes 2 order IDs, and each of them has their own medication name. So the sort of grandparent of all of these hierarchical databases and how they're used in healthcare is, of course, MUMPS. This was the original paper published in 1969 by Bob Greenis and Octo Barnett from the Mass General Hospital, who described the Mass General Hospital Utility Multi-Programming System, aka MUMPS. Again, described in 1969 by Greenis, Papalardo, Marble, and Barnett. That's the acronym and what it stands for. And the stated goals of MUMPS, this is directly from the paper, was that it should provide a flexible interface, including, like, for example, something could be used as a lab system for composing notes and for variable outputs. It should be able to handle variable length text. It needed to have a hierarchical design to support the complexity of clinical data and the various update and retrieval methods that we need. It needed to support multi-user access. So the original paper actually recognized that there was a potential for conflicting updates and sort of anticipated that we needed to have what's called an ACID transaction, and I'll describe what ACID transactions are later. It needed to have large storage capacity, low CPU usage, even in relative terms back in 1969. And ideally, it should have a high-level programming language that was English-like or useful enough to allow people to make interface design less time-consuming, more efficient, not requiring full-on assembly language or machine code. So MUMPS was eventually renamed to just M in 1993 by the M Technology Association. It was recognized as an ANSI standard in 1995. MUMPS and its derivatives now include InterSystems Cache, which many of you might recognize as the hierarchical database used by some of the larger EHR vendors in the country today. Cache, coincidentally, and these hierarchical databases are also used in the financial services sector, where they have a similar design requirement of being able to pull up every attribute about a single entity very quickly, like all the transactions that were conducted by a single customer. Interestingly, MUMPS actually predated something called the NoSQL movement. In recent years, like in the past 10 years, there was this movement to get away from relational databases because of these limitations on highly dimensional data, and what people have now called a schemaless DB. It's of course ironic that the original motivation for this was recognized in 1969 in the creation of MUMPS. And it's especially ironic when you hear, I think, well-meaning pundits talk about how outdated the database systems are that run our electronic health records. I think that's a misinterpretation of what these databases are good at and why they were chosen for this specific function of running an EHR. So MUMPS is a procedural language. It has its own procedural language. You can see the line numbers here. This is a sample snippet of code. It's 2 lines long, line 1.10 and 1.15. And you're not going to be expected to know the sequence or the syntax. But basically what line 1.10 says, go to the command prompt and read from the user input, show the phrase unit number followed by a space, and expect an input from the user, assign it to the variable x. And then in line 1.15, if x matches this pattern, 3 numerals followed by a dash, 2 numerals followed by a dash, and then 2 numerals, then go do something else. But if it does not match that pattern, then type the phrase on the screen, illegal. And so if you run that program, so he wrote a program, write 1, and then wants to execute the program, so he says do 1. If you do 1, and by the way, in this screenshot, everything that the user is typing in is underlined. So the write 1 command, the do 1 command are things that the user has typed in. So if I do 1, if I run that program, it says unit number. I type in 123-45-678. That does not match the 322 pattern that's expected in line 1.15, so it shows me the word illegal and takes me back to line 1 again. And so I type in 12-345-67. It says illegal and kicks me back again. 123-456-78, illegal, goes back again until finally I get it right. So this one line of text, this little if-then pattern here, actually is a form of data validation. It's enforcing that I'm typing in presumably what's like a medical record number or something in the correct format that the system expects. So here's a more elaborate example, and take a look at this for a second. You can pause the video for a minute and guess what these snippets do. So the hint that I provided here is that imagine that this is a code for a user interface for a lab system, a lab information system. Basically it sets an array of values that's called the DCT, and it includes things that look remarkably like abbreviations for lab tests: calcium, phosphorus, FBS, what would that be? Fecal blood, maybe? Cholesterol, total protein, sodium, potassium, chloride, and so on. And then it's going to go to the command line and expect an input from the user. It'll say, read from the command line, show the prompt test, and assign whatever the user types into the value of the variable TES. Now, there's an interesting for next loop in here. It says, for I equals 1 to 14, incremented by 1, and if each piece of that DCT array with the index of I is equal to test, or if any piece of that DCT array with index of I is equal to the variable TES, then you can jump down to 2.3 where it asks for the user's result. But if it's not recognized, then go back to the prompt again and type in question mark, question mark, question mark. So in other words, it's asking you which test are you entering a lab result for. And if you happen to type in an abbreviation that matches that array, any member of that array of 14 elements, then allow them to type in the result, otherwise prompt them again. So this is also sort of a verification or validation of user input. The interesting thing to me here is that if you ever wanted to expand your panel of testing, you'd actually have to change 2 lines of code. You'd have to change line 2.05 to expand the number of tests that you've got there, and you'd have to change the iterator in line 2.20 because now you'd have 15 tests and not 14. And you can work through sort of what happens here and follow the underlined statements to see what happens. You can see when they do program number 2 and they type in MA, it throws an error and throws you 3 question marks. Like, what are you talking about? So until the user types in NA, and then it prompts them for the result of 125. Then they talk about adding another constraint where maybe there's some boundary condition checking. Maybe I want to flag any values for sodium that are less than 130 and greater than 150. So I'm typing in NA, I type in a result of 125. It says, this is probably an error. Is that okay? And I type in yes, and then it accepts it and allows me to go to the next one. So this is like 12 lines of code for a rudimentary laboratory information system. Kind of cool stuff. And in the original manuscript, they showed this diagram, which should remind you of that hierarchical database diagram from a couple of slides ago. There's a master patient file, a global array that's represented by this up arrow that later became a caret. Every patient is indexed according to a specific number, and if you tunnel down to that specific patient, Now you've got all the individual attributes of the patient. There are a list of laboratories, there are a list of diagnoses, there are a list of whatever. And if I go further down into their diagnosis array, I can see there's the 1 through J diagnoses in that array as well. So again, they were anticipating that clinical data needed to have a representation format that was highly dimensional and that allowed for the richness of clinical data that we expect to see in practice. So let's talk about this mumps global variable a little bit. In the original manuscript, Greenis and colleagues recognized they needed a hierarchically organized, symbolically accessed structure that was organized in key value pairs. They wanted to allow for local variables that were unique to that program, but also a global variable which would allow you to look up patients from a master database, essentially. So this global patient array is, in this example of code, is called the APR. So I've got set caret APR UN comma name equals Doe comma John, and then also global APR UN comma age equals 34. So UN might be a local variable in my program that I've just defined elsewhere. Maybe it's the patient's medical record number. So I'm saying retrieve the patient APR global array, find the local variable UN that corresponds to this patient, and where there's a name attribute, set it to the value of John Doe, and where there's an age attribute, set it to age 34. So again, very similar to this idea of getters and setters and attributes and methods. If I wanted to update a specific chemistry panel, I'd find the patient by locating them according to their UN, find the test value by abbreviation, in this case chem, for example, for chemistry, and then traverse down to the result component, in this case N for sodium, and then I would assign it a string that includes the date, comma, and the test value. So that's what that last set statement is meant to do. Pretty cool stuff. So, we've talked about, I don't think there's a huge difference between hierarchical databases and object databases, except that in an object databases, in addition to sort of the multidimensional data you can store, you can also support other types of data like graphics and photos and videos and even entire web pages. If you go to the InterSystems Cache website, they actually advertise that Cache is an object-oriented database, not a hierarchical database. But I would argue that object-oriented databases are actually a type of a hierarchical database. Now let's talk about Unified Modeling Language, or UML. This is a standard tool set for describing the aspects of a database software and business processes. This is basically, UML arose out of the need and the desire for developers to be able to consistently communicate the product requirements and the specifications and the schemas and the classes and the attributes and all this stuff in a visual and easy to assimilate way. So there's a number of UML tools and diagrams that we're going to go through. The first one is called the class diagram, which you use to describe object-oriented classes, including their name, their hierarchies, their attributes, and their methods. Then there's the activity diagram, which is where you would show the steps in a sequence. You can think of these as basically a flowchart. And in fact, a UML activity diagram and a flowchart are often indistinguishable. Then there's something called a use case diagram. The use case diagram is often easily recognized because it's the one that has stick figures. But the goal of a use case diagram is to identify who the actors are, or the participants in various tasks, what goals they're trying to accomplish, and so what kinds of tasks they're collaborating to accomplish, and what the dependencies are between those. So if you take a look at this example to the right, you can see that this is basically a use case for a restaurant. There's a system boundary that defines kind of what the computer system is supposed to do. And there's 4 participants: the waiter, the client, the cashier, and the chef. There's this act of ordering food that has 2 participants. There's the waiter and the client, but they each have different goals. The client's goal is to place the order, and the waiter's goal is to receive the order. And so the 2 actors there each participate slightly differently to accomplish that task of ordering food. And no, actually, I said there's only two participants. There's actually a third. The chef also participates because that's the person who has to confirm the order so that they can cook the food. Another type of UML diagram is an entity relationship diagram. So this is, we saw this in the computer programming lecture when we were looking at the Smart on Fire, and we looked at the Fire resources and how they were represented both in JavaScript notation but also in a UML diagram. So ER diagrams described objects and their relationships. And with an ER diagram, a programmer can actually take that all the way through to build the physical schema of a database. So this is an example of a class diagram. And what I'm showing here is that there's a dog class and a mammal class. And the arrow indicates that the dog class actually extends the mammal class. I think a little bit counterintuitively, the parent class is the one that the arrow points to, not where the arrow is coming from. But I think that's just convention for UML class diagrams. And typically you have the name of the class at the top, and in the second box you have the attributes, and in the third box you have all the methods. So here you can see that the dog class extends the mammal class. The mammal class has its own attributes of the number of legs, where initially it's set to an integer of 4 and so on, and you can see the getters and setters. By the way, this is the UML class diagram for the Java programming example that we did in the programming lecture. Here's a UML entity relation diagram, or ER diagram, and what's being shown here with this, the part I wanted to highlight here was, like, if you look at the row that has customers, places, and purchase order, you can see a series of symbols, the 0, the 1, and the thing that looks like a crow's foot. Those are ordinality indicators. They tell you how many customers participate in this activity and how many orders they're allowed to place. So what that 0, 1, and crow's foot symbol represent is that 0 or 1 customers, but not more than 1 customers, can be involved in placing a purchase order. And they can purchase 1 or more orders. That's what the crow's foot represents. And you can see that the customer has those attributes listed above and the purchase order has those attributes listed above. From that ER diagram, this is another way to represent it. They can actually create the logical schema. So the create table customers, and that's, I could go directly from that top ER diagram to that bottom SQL code and create the schema from the data definition language. So in the mumps set of this talk, we talked about what the ACID test represents. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. An atomic transaction is an indivisible transaction. It either happens or it doesn't. So if I treat, let's say I'm trying to update 1,000 rows in my database, I need to be able to treat that as an atomic transaction. I cannot accept the state where only 500 of the rows get updated and then the other 500 fail. The entire transaction either takes place or not, and that's what's meant by an atomic transaction. Consistency means that the transactions must meet all the constraints. I cannot add a date to an integer field, I can't have a primary key that's not unique, and so on. Isolation is the principle that relational databases must be able to sequence simultaneous or near simultaneous transactions. You have to be able to avoid race conditions. You have to be able to avoid write failures where if the database actually receives 2 update requests at almost the exact same instance, it has to know, okay, this one's going to happen after this one, and I'm going to queue it up in such a way that I promise to isolate these transactions and not have one of them overwrite the results of the other, or corrupt the results of the other. And then durability is that the system must be fault tolerant. So for example, if you're trying to update 100 million rows in a database and suddenly the power goes out, when you boot up that system, it should have somewhere in the system a record of how far it got, and you should be able to roll back the transaction and then complete it under better conditions. Now we've got a few heady topics. Normalization, and I'm not going to spend too much time on these, but I do want you to understand kind of conceptually what normalization refers to. So we had all kinds of problems with that flat file. Namely, we were trying to put two medications into the same cell, and we needed a way to maybe separate the fact that Louise was on two medications from her unique attributes of date of birth and deceased status. And the problem with that flat file and the redundancy and the risk of putting those two meds in the same cell is that it violates something called first normal form. And normal form normalization refers to this idea that we can, through proper design, free the collection of relations from undesirable insert, update, and delete dependencies. We can reduce the need for restructuring the collection as we introduce new data types and therefore increase the useful lifespan of this application. We can make the relational model more informative to users, and we can make the collections of relations neutral to query statistics. So this is first normal form. I've taken that, let's say, actually this is an example of a database that's in first normal form. You can see that each cell contains a single value, unlike our flat file, which broke that rule, and that there's no duplicate rows. I've got 4 distinct rows with 4 distinct tuples. But this is in some ways susceptible to various insert, delete, and update anomalies. Specifically, the way I've constructed this table, I can't indicate that a patient has a preferred pharmacy without a prescription, unless I can create a row with null values. So in a weird way, it's conflating the desire to capture their pharmacy with the desire to capture their medication list. It also conflates the desire to have a medication list with whether or not that medication is on the formulary or not. So there's a lot of sort of messiness in how we've constructed this table, even though it's in first normal form. There's a potential delete anomaly here, that if I delete the medication acetaminophen by deleting that row, the first row, I lose the fact that patient 1001 has a preferred pharmacy of Glenbrook. And finally, if MedStar, the pharmacy chain, ever changes their name, we have to update it in multiple cells, which is not ideal either. So there's an update anomaly here as well. So the solution to this is to put it into what's called second normal form. And in second normal form, a database is said to meet second normal form if it meets all the criteria for first normal form and it meets this additional constraint that every non-key attribute is dependent on the primary key. In the first normal form example, we didn't really have a primary key. And so this notion that every non-key attribute is dependent on the primary key means that we shouldn't try to put attributes that relate to the pharmacy in here. We shouldn't put attributes like the pharmacy name. We shouldn't put attributes that relate to the medication in here. So now I've got an event ID for the primary key, a patient ID, a medication ID, and a pharmacy ID. You can see that even though this is technically a better engineered database, it's actually less useful for aggregate analysis. I have to basically rejoin all these data to their target tables to make any sense of this. But second normal form still has its own insert, delete, and update anomalies. We have not freed it from the constraint that we can't indicate a patient's pharmacy unless the medication is prescribed. If we delete the last row that contains 9906761 as the medication ID, we can no longer tell if it's on formulary or not. So in other words, medication ID has an attribute of formulary that's misrepresented here. And then finally, if we want to update the formulary status for a single medication ID, we have to update it in multiple places. So we have to get this to third normal form. We have to break it down even more and decompose it like this. So now this is in third normal form. It meets all the criteria of first and second normal form, and no non-key column determines another non-key column, which is a very simplified definition. But now we're starting to get something that's a little bit cleaner. I've got a list of medications on the far right with an attribute that tells you if they're on formulary or not. I have a list of patients in the middle with a list of their preferred pharmacies. And then I have a list of ordering events on the far left that includes which patient and which medication they were prescribed. So for most reporting use cases, third normal form is good enough. But even this has its own potential insert, delete, and update anomalies, which I'll let you read through here. There are technically higher forms of normalization. There's one called Boyce-Codd normal form, which is abbreviated BCNF. It's sort of the holy grail. It's above third normal form. But in practice, a database that's in third normal form, 3NF, can be called normalized. And they're safe against most insert, update, and delete anomalies. But just recall that even though it's a better and more durable long-term solution for how to store these data, if you want to use it for any aggregated reporting, you have to first denormalize the data. And so for high-performance relational database applications, you sometimes need to denormalize the data on purpose to allow for single-table lookups without having to do all kinds of additional joins. And this is the reason why there's a difference between your reporting database, your data warehouse, and your data marts. That the more useful you want the data, the more aggregated it needs to be, the more denormalized it needs to be. You can use simpler structures, and you don't care so much about which normal form they're in. And this is that same point made again, that there's an activity called ETL, or extract, transform, and load, which is the process of getting transactional data into a format that's optimal for reporting and queries. And a real-life example, if any of you are familiar with the Epic Electronic Health Record, it runs on InterSystems Cache, an object-oriented database for transactional processing. And then every night, there's a giant ETL process that kicks off that pushes all of the new data into a relational database. At our institution, that's an Oracle SQL database that's tuned for reporting and aggregation. So the first system, the Cache object-oriented database, is great for transactions and for taking care of patients. The second one is better for reporting. A data mart might be a subset of these tables that I've intentionally denormalized so that I can start doing some aggregate analysis. So for example, I might take the 20 tables that I need to be able to derive some quality measures around asthma care, and typically I can update those on a less frequent basis and summarize the data in that format in a way that allows me to do things like spreadsheets or dashboards or visual analytics. So for example, while I might do the ETL process from the transactional system to the data warehouse nightly, I might only update the data mart weekly or monthly, depending on what my needs are. Let's talk about network topologies. There's a lot of different network topologies, and these names I would suggest are very self-explanatory. The ones that's a ring is shaped like a ring. The one that's a line is a line. The one that's a star is a star. A fully connected one is one where every node is connected to every other node. Tree is a tree. Bus, we talked about in system integration in the programming lecture, that an enterprise bus, for example, is one where you have sort of a common backbone and all the nodes connect to that. But that's talking about system integration. This is talking about network connectivity. Here's a little bit more description about some of those. Let's talk about network protocols. Network protocols are amazing. They are the backbone of the internet. They're extremely vital and useful, and they all have a few things in common. So first of all, they require a handshake. If one computer program or system needs to speak to another one, if my browser needs to talk to a web server, it first sends a request and sends a handshake. And then it should ideally involve an acknowledgement of whether it received a payload or not. The packets that get transferred back and forth should include a payload. And it needs to be able to support a number of protocols, whether I need high reliability or whether I need fast streaming. There are a number of network protocols that support different types of internet usage. And I want to distinguish the network protocol from the data standard or the encoding standard. So if I'm sending lab results, I might do that as an HL7 version 2 message, which might be a simple pipe delimited text file, and maybe version 3 is the XML version of the same thing. And those could exist as the payload in one of these network messages. Both of those could be transmitted via TCP/IP as the protocol across a network. So TCP/IP doesn't care what the payload is. It doesn't care if it's an HL7 version 2 message or a version 3 message. So let's talk about TCP/IP. This is, again, this is the heart of the entire internet. The TCP/IP stands for Transmission Control Protocol. IP is Internet Protocol. There's another alternative protocol to TCP called UDP, which you need to know about, which stands for User Datagram Protocol. And the key differences between TCP IP and UDP is that TCP requires an acknowledgement, but UDP does not. TCP guarantees the sequence and the order of packets, and UDP does not. So, why would you want to use TCP to transmit data, and when would you want to use UDP? Well, TCP is used when packet loss is unacceptable. And in fact, the TCP protocol specifies that you keep sending it until you receive an acknowledgement, or you eventually time out. Whereas UDP cares less about acknowledgement and more about maintaining a steady stream of data. So UDP is used where packet loss is less important, and believe it or not, where packet sequence is also less important. So voice over IP uses UDP, for example. Many streaming protocols use it because I care more about avoiding stuttering and gaps, and I will tolerate a very slight jitter or decrement in call quality as long as there's not giant pauses while I'm talking or viewing a video stream. Which brings us to my first networking joke. Did you hear the joke about the TCP packet that walked into a bar? So it goes like this. A TCP packet walks into a bar and says, "Hello, bartender, I'm a TCP packet, and I'd like to buy a beer." The bartender says, "You're a TCP packet, and you'd like to buy a beer." And the TCP packet says, "Yes, I'm a TCP packet, and I'd like to buy a beer." And that's the whole joke, because the two of them had a handshake and an acknowledgement, and that was it. Networking jokes are hard to come by. I could tell you the one about the UDP packet, but you probably wouldn't get it. Wah, 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 wah. All right, all networking jokes aside, and I apologize, that was a horrible joke. Let's talk about the OSI 7-layer model. This is an important concept, and it's also eminently testable. The OSI 7-layer model suggests that the entire internet stack can be divided into 7 different layers, starting with the host layer and going down to the media layer. Within the host portion of the 7-layer model, there's data and segments. And they start from the top down. They go 7, 6, 5, 4, and then in the media portion of the OSI 7-layer model, there's the actual TCP packets and UDP datagrams, frames, and bits. So let's start at the top. At the data level, we're talking about the transmission of individual messages via the protocols that we've heard about: HTTP, which is the protocol that our browser uses, SMTP or FTP for file transfer protocol. At the application layer, there's a standard there, HTTP. Then there's a presentation layer or syntax layer, which is where I'm encoding the characters in a specific format. And for example, ASCII resides at this level. Or maybe this is where I do the data encryption. There's a session layer where I'm establishing a time period for which a certain set of transactions are valid, or I'm authenticating that someone is allowed to perform a transaction. There's a transport layer, which is where these segments actually get transmitted. Then there's the, by the way, that happens at the TCP and UDP, using TCP and UDP. There's a media segment where the TCP packets on the network layer get transmitted as packets via Internet Protocol through DNS servers and routers. There's the data link layer where I'm now transmitting frames of data that includes packets, that includes segments via Ethernet. And then finally, there's the actual physical layer, which is the actual mechanism by which these frames are transmitted via a copper wire or coaxial cable or fiber optic cable or whatever. And I think it's useful to think of these almost like a turducken, where frames can contain packets, packets can contain segments, segments can contain sessions, and all the way down to the actual HTTP message that's being sent back and forth. One of the things that might be tested is actually which protocols reside at which level. So I would stare at this for a little bit and try to commit these to memory. At the application level, the protocols I could think of were POP and IMAP for email, HTTP for web browsing, FTP for file transfer, SSH and HTTPS, which is the secure version of HTTP for secure browsing. Presentation layer, this is where encryption and decryption and conversion to character sets takes place. For example, switching from ASCII to Unicode in your browser. At the session layer, this is when you authenticate and establish that a session is valid for some duration. And the protocol that most of us are familiar with here is LDAP, Lightweight Directory Access Protocol. So Microsoft's Active Directory takes place at this level. At the transport layer, this is where we send TCP packets either with acknowledgement or UDP datagrams without acknowledgement. At the network layer, now you're talking about how Internet Protocol is assigning IP addresses and all the things that happen in your router, like assigning IPv4 or IPv6 Internet IP addresses to your devices, takes place here. The fact that your router uses dynamic host control protocol to basically lease those spots in the IP namespace takes place at this level also. So all of those IPv4, IPv6, and DHCP take place at the network layer. At the data link layer, the only one that I could come up with was ARP, the Address Resolution Protocol. This is used by TCP to communicate with hosts only when it can't reach them directly, but only through the neighboring hosts. And then finally, the physical layer. I couldn't think of a protocol that takes place at the physical layer, even though I'm sure there are some. The real-world analogy here is, again, kind of like a turducken, or in this case, like a post office. At the application layer, I send a letter to Bob. Bob receives and opens the letter. So on my end and on Bob's end, we're looking at a letter that we've either put into an envelope or taken out of an envelope. At the presentation layer, my letter is encoded in the Roman script using the English language. At the session layer, I've now put one or more letters into an envelope, which you can think of as like a session. And as long as I have the appropriate postage, the session doesn't care how many letters are in there. At the transport layer, this might be where the post office finds that there's a typo in the address. They mark it as recipient unknown and they send it back. I cannot get I might be able to get a confirmation of receipt or not if it's registered mail. If it's bulk mail, I wouldn't get a confirmation at all, and I don't really care. At the network layer, maybe this is where all of these letters are put into these big parcels and shipped by plane between cities. And again, the pilot probably doesn't know how many boxes of letters are in the back of the plane. Doesn't really care. All he or she knows is that they're trying to go from one city to the next. At the data link layer, the post office worker drives a truck between cities to deliver the messages. And finally, at the physical layer, what's being transported is ink or graphite on a piece of paper folded and tucked into an envelope. Telecommunications has expanded dramatically in the past 10 years. And it's basically changed the face of healthcare. You know, we have Wi-Fi devices are ubiquitous. Mobile, everyone has a mobile device. We use voice over IP pendants or other kinds of technologies for real-time streaming stuff. We have secure messaging solutions. Video conferencing that depends on something called codecs. A codec is short for a coder-decoder. And it's basically a compression algorithm for different types of data, whether it's audio or video or something else. Photographs, for example. One of the more common codecs used for video transmission is the H.264 Scalable Video Coding, or SVC. It's also known as MPEG-4, and this is how you distribute content on the internet, like YouTube videos is often done in MPEG H.264. One of the things about codecs is that these are actually, if you think about them, they're like binning algorithms. They're data transformations. They can be lossy or lossless, which means that I might lose resolution if I downscale an image or an audio file. If I go from uncompressed CD quality audio down to 96 megabits per second MP3 file, it might sound like junk on my end. There's a number of short-range wireless standards that you should be familiar with. These all fall into the category of Personal Area Network, or PAN standards. These include RFID or radio frequency identifier and NFC or near field communication, RFID being one-way and NFC being two-way. There's also a little known Bluetooth spec called IEEE 802.15 for Wireless Personal Area Network, which is Bluetooth and Infrared Data Association, or IRDA. I don't think I've ever seen anything that uses IRDA. The Bluetooth standard itself has a interesting evolution that it's 802.15.1. It was the original IEEE standard for Bluetooth, maintained by the now it's more recently maintained by the Bluetooth Special Interest Group. There have been some recent innovations in Bluetooth. Bluetooth 4.0 standard introduced something called Bluetooth Low Energy or Bluetooth Smart. And this standard, the LE or Smart standard, has become extremely popular in health and fitness devices and in patient monitoring devices. So Fitbits and those kinds of things, glucose monitors, thermometers. This minimizes the cumbersome steps of trying to pair the device. And Bluetooth Low Energy consumes much less energy, as its name implies, and it's great for these kinds of uses. So you'll see a lot more of these in the years to come, but be aware that this is the protocol that's used by many of those patient devices like scales and speed sensors and cadence sensors on exercise bikes and heart rate sensors and things like that. Now come the wireless standards, and I would familiarize yourself with these, at least the sequence that they go in, from B to G to N to AC, because that's also the order of speed. B being the slowest, which was very popular, back in like the 90s and 2000s. Then came along wireless G, which would supported bandwidths up to 54 megabits per second, but used the same frequency bands as 802.11b. And does interfere with things like microwave ovens and Bluetooth devices and cordless phones. So it's sort of a cluttered radio space to try to pack all these devices. I remember having a 802.11g router, and my devices would cut out every single time I tried to microwave something. The next bump from that is the 802.11n standard, which uses a completely different spectrum of frequencies in the 5 gigahertz range. It uses both 2.4 and 5 gigahertz for maximum speeds of up to 54 megabits and 600 megabits per second, respectively. You can boost the speeds even higher using something called MIMO, multiple input, multiple output. And then there's the newest standard, or the current standard of wireless AC. There may be some draft standards beyond AC, but AC is the one that's is very ubiquitous. For a gigabit Wi-Fi, this is up to 1 billion bits per second, or 1 gigabit per second. In the long-range wireless standards, these are all of your cell phone protocols, and unfortunately these are a little bit conflated by marketing, but because you see things like 3G, 4G, and 4G LTE. But be aware that when you see CDMA, 3G, 4G LTE, those are long-range wireless standards, typically used in like cell phone signals. So what are some of the wireless applications in healthcare? Well, there's IP telephony. Like there's a manufacturer named Vocera that makes these voice over IP pendants that you can use in healthcare. There are SMS text messages, although these are not secure and they are frowned upon for, actually they're illegal to use for patient identifiable information if you're trying to transmit them between providers because they're not HIPAA compliant. I think that they are potentially usable if you're discussing with a patient directly, because you presumably have the patient's authorization. But now there are secure texting solutions that are HIPAA compliant that don't use the SMS standard. Also, we're seeing an increase in the use of RFID and NFC tags for medical devices and even patients. We cover RFID standards in more detail elsewhere, but these are very, very tiny. There's a typical RFID chip that's used this is an implantable RFID chip used in veterinary medicine, compared to a grain of rice on the right there. RFID comes in 3 different flavors: passive, active, and battery-assisted passive. Passive actually relies on the power from the reader itself. So when you pass the RFID chip next to the reader has to emit a signal that's very strong, but it's strong enough that it can actually power the chip itself. RFID tags can be read-only or read-write. The RFID reader sends a signal to the tag to interrogate it, and the chip responds with its ID plus any other information that it's been tracking. So these are used for things like animal tags and smart cards and other kinds of asset tracking. And these can be passive, meaning that if I stick one of these RFID chips on a medical device, I can track its passage throughout the hospital. NFC is near field communication. This is the standard that they use for contactless payment. For example, if I'm trying to use Apple Pay at my local grocery store. And basically, the two devices have to be in close proximity to one another in order to transmit something like credit card data. Some of our biggest challenges with regards to all of these technologies is that, man, these are advancing way faster than we can keep up with. And so we have buildings that are built in the 90s or 2000s that did not and could not have anticipated the proliferation of these kinds of devices. So retrofitting older facilities with these kinds of equipment and dropping Cat5 cable across your hospital can be an expensive and time-consuming ordeal. In addition, memory is getting cheaper and cheaper, and the desire to have richer and richer information at the point of care is increasing. So now we're running into bandwidth limitations, where something like an MRI of your wrist might be 5 megabytes, but a CT 3D reconstruction of your skull might be up to 120. A CT angiogram could be like 230. The human genome is almost a gigabyte. I've seen stats as high as 1.5 gigabytes. And so we run into challenges with how to balance the compression of these with the actual quality that you receive. And a little known secret for those of you that are not radiologists might be that the image that you see when you're looking at your diagnostic modality viewer, your PACS system viewer on the clinical units is very compressed compared to the version that the radiologist sees at their dedicated PACS workstation. And that's specifically because it would take a ton of bandwidth to push those images all the way across the images. You'd basically be waiting for much longer time to pull up an X-ray or something like that. And so they take advantage of the fact that most of us don't have the ability to discern the films the way a radiologist can, and it's for our purposes. If we're not radiologists, it's okay. We would tolerate a little bit of compression artifact in order to have the ubiquity of access. And so keeping up with more and more of these ologies, now we're talking about 3D reconstructions and cine loops if you're a cardiologist, or if, now we want to store audio or video files. And maybe in my mobile electronic health record app, I want to be able to capture a patient's limp as a video file and store it with their electronic health record. So we're distinctly getting challenged in many ways to keep up with the clinical demand for these technologies. That also brings up the question of network security. We have to partition our network at our institution such that we have a guest network for patient use that doesn't collide with the protected network for our medical devices, that does not collide with the network that we use for our laptops and things like that. And we also have to be able to provide a VPN and remote access. With these different tags that are passive, that you can basically tap to log in or tap to pay for something, they do pose concerns about what's called skimming, that if I come into proximity with something, someone might be able to find out information about me that I don't want to. Most institutions now support bring your own device, recognizing that they cannot keep up with cell phone technologies as fast as the telecom manufacturers can. So they basically say, you know what, as long as you allow us to remotely manage your device by putting some software on it, you can bring whatever device you want. And that bring your own device strategy has extended, at least to my institution, to phones. They do recommend it for laptop. They allow it for laptops if you buy, for example, a research funded laptop, as long as it's imaged by our IS folks with the correct software. They don't care if it's a PC or a Mac, they'll do it for you. The last vulnerability that I'll mention, and probably one of the most important, is that as we become increasingly dependent on networked devices and computer programs and cell phones and pagers, or not pagers, but secure communication methods, uptimes become critical and downtimes become very, very dangerous. So if your institution is highly tech dependent and they're not practicing good simulations of downtimes, then you're running a huge risk the first time your system comes crashing down because of a malware threat or a ransomware threat or whatever. So that's the end of this lecture. Thanks for listening. I know it was a lot of content to cover, but I hope you enjoyed it. Here's the additional reading. I've listed for your reference specifically the original Mumps paper from 1969, which I encourage all of you to look up. I think you can find the PDF on PubMed for free. If you want to learn more about SQL, please do some of these tutorials. There's some great SQL tutorials out there that will coach you through all the stuff we covered and much more, and in much more detail also. So there's the W3 Schools website that includes SQL. Remember from the programming lecture, they also have a tutorial on JavaScript. There's SQLzoo.net, which has a great tutorial on SQL, and I would encourage you to do it. You can expect to see at least a couple of questions about SQL programming on the exam, so please make sure you study that. If for whatever reason you're a glutton for punishment and you want to learn more about database normalization, there's a nice lecture on it at this website listed here. Thanks for listening.